The first screen is composed of 6 menus located at the top of the window, and 4 GUIs. The Site Conceptual Model Information GUI is a GUI that generates meshes using shapefiles produced from GIS and borehole data. The Geometry Mesh GUI allows for the manual configuration of the mesh and designates nodes, elements, and element sides for the spatial information of initial and boundary conditions. The Model Parameter Input and Simulation GUI is for entering material properties, initial values, boundary values, time step sizes, and information necessary for numerical simulations, and it also conducts the numerical simulation. The Visualization GUI outputs the numerical simulation results in the form of graphs or contours or the form of an ASCII file. We list all available benchmark 2D/3D examples. For example, you can click each benchmark item to get the detailed information about this problem. To start a new project, select Project and click New. Then, enter the project name. For benchmark problem 1, since it is a 2D numerical simulation, select THMC 2D in Model. Then, click Confirm. Select Geometry GUI. To start a new solution, select File and choose New or Open Solution. You can define the area of interest by selecting different domains, depending on the problem. For example, in problems involving gravity, you might select the ZX plane. Click on the square tool located on the left side of the window. A panel will then appear. After entering W equals 50 and H equals 200, click on the Preview button, followed by the Create button. When you click the Create button, an area of interest measuring 50 by 200 appears on the window. Click on the Mesh Generator tool located at the top of the window. In Benchmark Problem 1, the area of interest is composed of rectangular elements. Therefore, in the Mesh Generator window, click on Quadrilateral. After clicking on GEO, D1, N4, D1 means 1 domain and N4 means 4 nodes totally. In the panel located selecting Domain 1, you can see that 4 edges and 4 BGs, BG means boundary group, have been created. Since the area of interest is divided into 41 nodes in the Z direction, right-click on BG1 and input the Set Nodes Count to 41. Then, click the Set Nodes Count button again. Since the X direction consists of 2 nodes, right-click on BG2 and set the nodes counts to 2. Click on the Mesh Generator tool, and in the Mesh Generator window, click on Quadrilateral. The result of dividing the area of interest into 41 nodes in the Z direction is illustrated. If the mesh has been created, one would want to set initial and boundary conditions for the area of interest. In Benchmark Problem 1 for the initial condition, since different values were input for the top, bottom, and the rest of the area of interest, we will specify initial conditions for each of these 3 parts separately. First, with Add Selection selected on the left side of the window, choose Select Nodes. Select the nodes located at the top of the area of interest, and drag to select the 2 top nodes. The window screen appears. In the panel, select Create Group, then the Create Group window appears. Click on the list box next to 2. Simulation category, and select Hydrological. Then, click on the list box next to 3. Condition name, and choose Initial. Then, click on Assign to Group Name. If you enter top into the text box under 3. Asterisk group name and number, the result will appear. Then, click on Apply and Close. To set the initial conditions for the nodes located at the bottom. Setting the initial conditions, select all nodes except those at the top and bottom. Then, we will explain how to set the boundary conditions. In benchmark problem 1, we set a variable boundary condition for the top and a Dirichlet boundary condition for the bottom. First, to set a variable boundary condition for the top, with Add Selection selected on the left side of the window and Labeling Vertex selected on the upper side of the window, choose Select Edges. To select the element side located at the top of the area of interest, drag to select the top element. Then the window screen appears. To verify the selected boundary element sides, click the tool located at the bottom of the panel. The boundary side corresponding to the top boundary side is node 82, 41. Therefore, boundary sides node 81, 82, and node 41, 40 should be removed. Select the boundary sides node 81, 82, and node 41, 40, right-click, and choose Remove Selected Mesh Objects. Then, in the appearing warning window, click OK. Select the Create Group tool located below the panel. Shape type has line selected. 4.2. Simulation category, choose Hydrological. Then, 4.3. Condition name, select Variable. Click on Assign to Group Name and type top under 3. Asterisk group name and number. Finally, click on Apply and Close. Thus, the variable boundary condition setting for the top boundary side is completed. The process of setting the Dirichlet boundary condition is very similar to the process of setting the initial condition. The only difference is to select Dirichlet for condition name. We have completed the mesh generation for benchmark problem 1 and finalized the settings for nodes and element sides for the initial and boundary conditions in the Geometry Mesh GUI. After setting the initial and boundary conditions for benchmark problem 1, the subcategories are created under the condition category. You can click on each subcategory to verify if the selection has been made correctly. Lastly, to save the mesh information, initial and boundary conditions set, click the Save Solution, then, in the Save Geometry pop-up window, click OK. The Model Parameter Input and Simulation GUI consists of 4 major functions: Import Mesh and Boundary Data, Start Model Simulation, Stop Model Simulation, and Restart, as well as 4 tabs: Parameter Wizard, Simulation, Global, and Hydro. To import the mesh information and the initial and boundary condition settings entered in the Geometry Mesh GUI, click on the Import Mesh and Boundary Data tool. Then, the Mesh Import window pops up. Choose CM in the unit and click on Import. To proceed with the numerical simulation, select the Advanced option in the View menu. Enter the project description and unit in the Parameter Wizard tab. For benchmark problem 1, the units of cm, g, and day are used, so select the corresponding units. Then, in the module, select Fluid Flow and choose the Transient Fluid Flow option. Click on the Time Preview button. This action will prompt a pop-up window of Simulation Time Setting. Change parameter for benchmark problem 1. To check if the time step size has been entered correctly, click the Preview button. Then, click on the Save button. To input the material properties, click the Edit button under Material. This will bring up the Material window. The domain is assumed to contain soil with a saturated hydraulic conductivity of kxx equals kxc equals 0 cm per day and kzz equals 10 cm per day, a porosity of 0.45, and a field capacity of 0.15. Consequently, when the material pop-up window appears, check hydraulic conductivity next to flow property. Additionally, enter the following values. Click the Edit button located beneath Water Retention Curves, then the Water Retention Curves window will pop up. In benchmark problem 1, the unsaturated characteristic hydraulic properties of the soil are given as. Click Confirm to close the Water Retention Curves window and click the Save and Close buttons to exit the Material window. Clicking Edit. When you click the Edit button, the Initial Boundary/Source Sink window will pop up. The initial conditions are set as follows. A pressure head of -90 cm is imposed on the top surface of the column, 0 cm on the bottom surface of the column, and -97 cm elsewhere. Input the initial conditions. Select Hydrological/Initial Condition in the list box for the spatial type and then click the button. After that, in Conditions, select Hydrological Initial Top, Hydrological Initial Bottom, and Hydrological Initial Rest in sequence. Then, enter the corresponding initial values into Initial Pressure. Choose Hydrological/Dirichlet Boundary in the list box from the spatial type, then click the button. In Conditions, select Hydrological Dirichlet Bottom and click Edit button. Clicking the Edit button, the Profile Input Form window will pop up. Click the button next to Profile and type 0 and 04 total heads and data points. Select Hydrological/Variable Boundary from the Spatial Type drop-down menu. Then, click the button, and in the Conditions section, choose Hydrological_Variable_Top. Enter 04 ponding depth and -94 minimum pressure head. After that, click the Edit button to input the profile. Enter the values for time and rainfall/evaporation rate. Then, click the Save button to close the Profile Input Form window, and click the Save and Close buttons to exit the Initial Boundary/Source Sink window. In the Hydro tab, you can view and modify inputs related to iteration and optional parameters, material properties, initial conditions, sink/source, and boundary conditions. Since benchmark problem 1 simulates the vertical flow of fluid, it should be set as from data set 3 to flow record 4, set kgrav equals 1. For matrix solution, choose the direct band matrix solver, IPNTSF equals 0. Furthermore, since the tolerance is set to 0.02, configure it form data set 3 to flow record 6, set TOLF equals 0.02, TOLBF equals 0.02. The input for the model parameter input and simulation GUI has been completed. Now we see Start Model Simulation located on the upper left side of the program. You can also click Stop Model Simulation to interrupt the simulation or restart to resume the simulation from the last step. Or you can click Select button beside the Restart step to choose the step to continue the simulation. The simulation will start with the PowerShell window with better performance. Or you can uncheck the Start with window to show Login window on the downside. Once the numerical simulation start, you can check the current simulation process status in PowerShell window or log window. If something wrong and need to debug, you can check files in the model input block and model output block. The model input block include model input file, mesh file, maximum file, and time input file. The output module block includes simulation log, elapsed time log, and iteration log. And you can check the last message of log window and the last message of simulation log as the first step when debugging. You can also turn on the advanced model by click Advanced of View menu bar. Thus the simulation will stop in PowerShell without closing. Then you can see the error message or manual start the model execution in PowerShell. There's Draw button beside the elapsed time log. You can click it to show XY plot for the accumulated elapsed time chart. On the left menu of the application, click Visualization GUI. In the Visualization GUI, locate the Add Task button, represented by a plus sign, at the top of the panel and click it. A new task will appear in the Visualization Tasks list. Check the checkbox at the beginning of the new task. Click the Start button, represented by a play icon, at the top of the panel, to begin the conversion. The status of the task will change from unstarted to completed. Once the conversion is finished, click the Open button next to the PowerView button on the selected task. A PowerView window will open, displaying a mesh with color-filled elements. Click the Open button next to PowerView. This section introduces basic concepts and utilities of PowerView for analyzing your visualized simulation results. The main visualization panel is located at the center of the window, displaying the colored mesh. Various toolbars are positioned at the top of the PowerView window. Locate this example in the folder of Pipeline Browser, Tree View. This menu on one of the toolbars at the top of the window that lists all variables from your simulation. Select any variable from the list to change the simulation variable result for visualization. Find the Time drop-down menu in one of the toolbars at the top of the window. Use this menu to select specific time steps from your simulation. The main display panel will update to show the visualization for the selected time step. Locate the Playback Control toolbar next to the Time drop-down menu. Click the Play button on this toolbar to automatically advance through time steps. This feature allows you to view the visualization results as an animation. For example, you can play the animation in this case for pressure value changes. Special notes: experiment with different variables and time steps to gain a comprehensive understanding of your simulation results. The playback feature is particularly useful for observing changes over time in your data. Click Plot over Line, then the graph will show the line. Click Z-axis, the line segments in the graph will become vertical to the XY plane. Click the visible icon, indicated by eyeball, on the left side of the tree view nodes, then click Apply. A line chart will appear on the right side window of the screen. Proceed to click on Filters, followed by Temporal, and then Force Time located in the top menu bar. Next, input the appropriate time step values. The window in the lower left corner can configure the property of chart that provides the option to redefine the labels for the left axis title and bottom axis title. Click Apply, then click the visible icon, indicated by eyeball, next to Force Time 1. For the first checkbox below, a single click will select all items, while a double click will deselect all items. Select Pressure to display the pressure line. Disable the visible icon, indicated by eyeball, adjacent to Plot over Line 1 so that only the pressure line is visible on the right side of the screen. Rename the pressure line to T equals 0.11 days. By scrolling down, you can modify the line thickness, line style, marker size, and chart axis properties. Sequentially select Plot over Line, Filters, Temporal, and Force Time. Then, repeat the previous line plotting steps, ensuring that the only modification is the adjustment of the corresponding time step values. With 4 pressure lines now displayed on the right side window, the graph may be too complicated. To simplify the view, click Split Vertical Axis, and then select Line Chart View in the lower right corner of the window. At this time, a line chart will be generated on the right side of the window. Select Plot over Line 1 from the left side of the window, then proceed by selecting Filters, followed by Temporal, and Force Time. Enter the force time value as 10.05. Finally, click Apply. Click the visible icon, indicated by eyeball, next to Force Time 5, and several lines representing different physical variables will appear in the chart at the bottom right. Double-click to deselect all parameters, then select Pressure. Change the legend name to T equals 10 days. Scroll down to choose different line styles. Repeat the previous steps to draw different lines. Select Annotate Time 1 on the Tree View node. Then, sequentially choose Sources, Alphabetical, and Text from the top menu. Upon completing these steps, Text 1 will appear in the left panel. Repeat this process to create Text 2. Enable the visible icon, indicated by eyeball, on Tree View node for Text 1. The text will then appear in the window. You can adjust the text position by scrolling down to the Text Position section. Click on Text to modify the title of the graph. After making the changes, click Apply to update the title, which will then appear in the window. To change the title of the lower graph, repeat this process in the lower right window.